So today we're going to be going through and working on the chain rule. This is section 3.7. So we're going to focus on learning how to do this. This is another way of taking a derivative. So we're going to start out just kind of defining it. So we have a theorem. It says if f and g are differentiable, so if f and g are differentiable, then the composite function f composed of g of x, which we'll remember is f of g of x, that is differentiable and the following thing is true. We get if you try to take the derivative of f of g of x, then that equals the outer function f's derivative, leave the inner function alone, then you multiply it by the derivative of the inner function, and they call this little g prime part, they call that the inner derivative a lot of times. Okay, so we're just going to go through and do some examples. So first one they want us to do, they give us y equals cosine of x cubed. They basically want us to find y prime. So, let's see here. Let's use a different color. So, for solution on this, cosine is acting as f. So when we want the derivative, cosine's kind of the outer function. It's sort of acting as the f. X cubed is the inner function, so we'll take the derivative of cosine, because that's what f prime says to do. Derivative of cosine is negative sine. We leave the g of x function, leave the inner function alone, so we leave the inner function alone, and then we multiply it by g prime, which is the derivative of the inner part. The inner part here is x cubed, so we're going to multiply that by a 3x squared. And that will be our derivative by the chain rule. So next one they want us to do. So they're all going to kind of have the same sort of pattern where you identify who's the outer, who's the inner, and then you multiply it by the derivative of the inner. So we get y equals the square root of x to the fourth plus 1. And they want us to find y prime again. So we'll say, okay. This time the square root is acting as the outer function, and the x to the fourth plus 1 is acting as the inner function. So when we take the derivative, we want to take the derivative of the outer function, which is the square root. Square root's the 1/2 power, so we're going to use the power rule and say it'll be 1/2 times some stuff to the negative 1/2. And what goes in here is the inner function left alone. So the inner function is x to the fourth plus 1. So we put the inner function in here left alone. Then we have to multiply that by the derivative of the inner function. Again, the inner function is x to the fourth plus 1. If you take the derivative of x to the fourth, that's 4x cubed. The derivative of 1 is nothing. And this right here will be our derivative. So let's take the derivative of the outer function, leave the inner function alone, then multiply by the derivative of the inner function, which we call the inner derivative, and that's how the chain rule is applied. So let's move on to the next couple. So this time they want us to do find dy dx dy dx for y equals tangent of x over x plus 1. Okay, so for our solution here, tangent is the outer function, so we'll take the derivative of tangent, which will become secant squared. We'll leave the inner part left alone. Then we need to multiply by the derivative of the inner part, and that's going to require the quotient rule. So I'm going to write out d dx to show that we're trying to take the derivative of the inner part, because I want to write out the statement for the quotient rule. Quotient rule is bottom left alone times the derivative of the top minus top left alone times the derivative of the bottom, all that over the bottom squared. So we're going to use that to take this derivative here. So dy dx equals, it's secant squared of the inner part left alone. And now to take the derivative of the inner part, that's the inner derivative, we're going to use this formula here. So it's bottom left alone, derivative of top, minus top left alone, times derivative of the bottom, all that over the bottom squared. And we'll say, okay, that is our derivative. Oops, I made a mistake. Hang on. It's bottom left alone, derivative of top, minus top left alone, times the derivative of the bottom, which would just be 1, all that over the bottom squared. And we clean it up a little bit. So this right here will be the top part here. If we look at kind of what's going on at the top here, it's x plus 1 times 1 minus an x. So the x's will cancel, so we'll end up with just 1 over x plus 1 squared. And we could say that that's our derivative. Okay. So they're going to note in Leibniz notation, if we start with y equals f of u, and then the u is g of x, this would be the same as f of g of x. In Leibniz notation, if we did dy dx of this expression, so if we did kind of this f of u and then the u is a stand-in for g of x, if we did dy dx of that expression, this would be f of u times the g prime, so it would be f prime of u times the g prime of x if we took the derivative from the chain rule, because you could say f of u, that's the outer function with the inner part left alone, times the derivative of the inner part. So in Leibniz notation, this looks like we could say this would be df du, and then it would be du dx. So we could say the chain rule in Leibniz notation, dy dx, we could say that this would be dy du times du dx. So this is kind of chain rule in Leibniz notation. Okay, so we'll do a couple more examples, and then we'll generate a couple of equations. We'll have us generate some equations, and you can either memorize the equations or just have the chain rule down and just use the chain rule for it. So example 4, we have a sphere of radius r. and it increases at a rate of 3 centimeters per second. Okay. At what rate is the volume? So at what rate is the volume increasing? Or is the volume changing, I guess? We don't know if it's increasing. Or I guess it is increasing. Volume V of the sphere increasing when R is 10. So what we're basically going to do here is we're going to use the volume equation. So the volume equation, volume equals, let's see, what is it? 4/3 pi times R cubed is the volume equation. We're going to assume that R is a function of t. So when we want to go and figure out the derivative of this thing with respect to t, we want to know what's the rate of the volume changing with respect to time. We're going to take the derivative of this with respect to r, and then we're going to view r as a derivative of r with respect to t. So what we're basically going to do is we're going to do the change in the volume with respect to r, and then we need to know what's going on with the change of the rate with respect to t. So what this is going to have us do is take ddr of our volume equation, and then we need to multiply that by dr dt. So ddr of this, the 3 will come down, it'll cancel with the 3 there. We'll get 4 pi r squared times dr dt. And they tell us the radius increases at a rate of 3 centimeters per second. So that tells me the radius here is increasing at a rate of 3 centimeters per second. At what rate is the volume of the sphere increasing when the radius is 10? So the radius is increasing at 3 centimeters per second. And we're saying, okay, how big is the sphere? What rate is it increasing whenever 10 is plugged in there? And so what we get is 4 times pi times 10 squared times 3. So 4 times pi times 10 squared, it's 100, times 3, ends up being about equal to 37, we'll round up to 70. This would be cubic centimeters per, so was it minute or second? Second. Cubic centimeters per second. So that should be about the rate that the volume changes in this situation. So we had to use that, kind of use the chain rule where we took the derivative of this expression with respect to r. Another way we kind of view this, so let's write out kind of a alternate way of getting this. In the prime notation, we have v equals, it's 4/3 pi, and we're going to treat r as a function of t. So when we want to take the derivative, v prime, we have to use the chain rule. The 3 comes down. You get 4 pi times the inner part squared. So that would be the r function squared. Then you have to multiply it by r prime, which would be the change with respect to t. And we can see that everything is going to kind of come out to be the same. R of t, we're looking at that when the radius is 10. And then r prime of t is the rate that changes, which is 3. And it ends up being sort of the same thing. So that's kind of seeing it in the prime notation. And this is kind of viewing it in Leibniz notation. So moving on to that last couple of ideas here. And then we'll generate some equations for stuff. Alright, so this is example 5. And example 5 wants us to go through and say if y equals x squared plus 7x plus 2, and so y equals x squared plus 7x plus 2, and that is all raised to the negative 1/3 power. This is part A, and then part B gives us y equals e to the cosine, I think it's of t. In both these cases, we want to find y prime. So for part A, the chain rule is going to apply. We'll say y prime, the power is sort of the outer function. So the 1/3 power, or negative 1/3 power, is going to come down as negative 1/3. Inner stuff is left alone. That goes to the negative 1/3, take away 3/3, goes to the negative 4/3 power. And then we multiply by the inner derivative, which is the derivative of this stuff. And if we take the derivative of this, we get 2x plus 7. So that is our answer to part A using the chain rule. And then to part B, we'll get y prime equals, e is the outer function, it is its own derivative. So we get e to the cosine of t left alone. Cosine of t is the inner part, so we need to multiply it by the derivative of the inner part, which will be the negative sine function. Okay. And then we got one last kind of tricky example, and then we'll go back and generate a couple of quick things that you can memorize if you want. So this one here is going to have us use the chain rule a couple times. It wants us to find d dx of the square root of 1 plus the square root of x squared plus 1. So we'll say, okay, the first square root here is the outer square root. So when we do that, we'll get 1/2 times the outer square root derivative. So 1/2 comes down times the inner stuff left alone. So the inner stuff of the outer square root is sort of this stuff right here. So that stuff's going to be inside the square root function left alone. And then we need to multiply it by the inner derivative, which is the derivative of this inside stuff. And that's going to require the chain rule a second time. So this part here is done. For the, like this first block is fixed, it's going to stay. It's the outermost derivative. With the inner part left alone. Now we want to do the derivative of this. The derivative of 1 is 0, and when we get to the derivative of the square root part here, that's going to require a second chain rule. So we'll bring down the 1/2, we'll have the inner part there left alone to the negative 1/2, and then we'll have to multiply that by the derivative of x squared plus 1, which would be 2x. And then this whole thing here will be our answer. Okay, so wrapping up a couple things, we're gonna add a couple formulas in here that we can generate from the chain rule, or if you all want to memorize them, you can. But they want us to say, oops, we're out of space here, so let me clear up some space for us. They want us to say for these last couple things here, what if you had the derivative of a function g of x to the nth power? Well, if we think about it, n is the outer function, so we take the derivative of n using the power rule. So n comes down, it's stuff to the n minus 1 power. We would leave the inner part left alone, which is g of x, and then we would multiply outside by the inner derivative, which would be the g of x derivative. So this is an equation you can memorize, or if you use the chain rule, You can generate it pretty easily from that. We also have the derivative of, they said e to the g of x. So e is the outer function, it is its own derivative, so we'll get e to the inner derivative, or sorry, e to the inner part left alone, and then we'll multiply that by the inner derivative. And this is a second function that we generated using the chain rule, but you could also memorize it if you wanted to. And the final one that is saying what happens if we do d dx of f of kx plus b. So we would take the derivative of the outer function, which is the f in this case, so that would be f prime. We'd leave the inner part alone, and then we'd multiply it by the derivative of the inner part. Kx plus b is linear, so the derivative of a linear function is just the slope, so that would all get multiplied by k. And this is a last equation that you could memorize if you wanted to, or you could, if you know the chain rule, you can get all three of these pretty easily. So, like example, this one right here, this first one, we could have done, I think it was in example 5, part A, we could have done using this one here, and part B could have been done using that equation there. But we just kind of used the chain rule to generate it. But you could keep these as separate equations. So we're going to stop there for the day and go on from